Today we're going to talk about Newton's second law. Um, on Tuesday, we talked about Newton's first law, and that says an object with no forces acting on it, if it is at rest, it will remain at rest, and if it is in motion, it will remain in motion. And what this is saying is that forces are necessary to change motion. That does not mean that an object can only move when a force acts on it. Instead, it means that a force is needed to get an object to start moving, but it will keep moving until another force acts on it. A force is needed to start and stop motion or to change motion. So that's Newton's first law. Newton's second law says an object subject to multiple forces will undergo an acceleration. So let's look at this example first. We have a situation where a person is applying the same force to two different objects, a basketball and a car. Since there is a net force in both cases, there must also be a net acceleration. But the acceleration of these two objects is completely different, even though the same force is being applied. There is one other big difference between these objects, and that's their mass. Remember, mass is an intrinsic property of an object, and it has to do with how hard it is to get an object moving. Or to stop its motion. So it's easy for a person to move a basketball and much harder for them to move a car because they have different masses. So the forces are the same, but the masses and accelerations are not. And we can use this to see that acceleration of an object experiencing a net force depends on the force and the mass. So just because the forces are the same doesn't mean the accelerations will be the same if the masses are different. And what this looks like is actually an addition. Oh, wait, I have an additional thing on here. Sorry. Mass is how hard it is to get an object to move or to change its motion, to start or stop its motion. Sorry. Anyway, now this is something we can add on to Newton's second law, and it is the net force on an object, which net force is just this vector sum of the forces acting on the object, is the mass of the object times the acceleration. And just the net force, again, it's the vector sum of forces. So if we have a force to the right and a force going down, our net force is the vector addition of those two forces. And acceleration is in the same direction as that net force. Let's also quickly introduce the units of force, which are newtons with a capital N just capital N is how we label them. And we can look at where these come from. So it's kilograms times meters divided by seconds squared. Kilograms, that's mass. Meters per second squared is acceleration. So if you ever forget what newtons are, or if you forget what the units of force are when you break them down, just think about Newton's second law, which is mass times acceleration. Here are just some examples of forces of different objects in newtons. So US nickel is actually kind of funny, 0.05 newtons. A quarter cup of sugar is 0.5 newtons. 1 pound object is about 5 newtons. The weight of a typical house cat is 50 newtons. So my cats, which are bigger, are going to be more newtons than that. 110-pound person is 500 newtons, and it goes on from there. So just an example kind of to give you a baseline. And so here's that image from talking about net force, but bigger. So the acceleration is in the direction of the net force. So again, we have force 1 putting down force 2 to the right. And so the net force, which is the vector sum, is down and to the right, and the acceleration is in the same direction as the net force, so it's also down and to the right. So this is something we talked through in class on Tuesday, but we'll go over it again. And we're going to draw it as a free body diagram instead of just drawing the forces on the book. So we have a book at rest on a table. It is experiencing a normal force from the table pointing up and the weight force from the earth pulling down. So when we're drawing a free body diagram, we draw this on an XY plane like this. And we set the origin to be the object. You can just put a dot there. And so the normal force points up, the weight force points down. So then the next thing to do with this information is we can generate equations, because we know that the net force is equal to the mass times the acceleration, and the net force is just the vector sum of forces. So the net force in y is the mass times the acceleration, and that's just the normal force, which is up, so it's positive, and the minus the weight force, which is down, so it's negative. So that's the net force in y. And in x, because there aren't any forces, it's just, oh, sorry, that one's supposed to be x. Got y there instead. But the net force in x is 0 because there's no forces acting in x. And we're going to do a quick example of how we kind of generate these things. So 1 sec. Okay, now we want to look at a box being pulled up by a rope and the box is accelerating upward. So I drew it already. The rope is on top of the box and then pointed the direction of its acceleration. So first, let's list the forces acting. So there's a rope, which means there's tension. And there's no surfaces, so there's no normal force. There's not like a rocket engine, so there's no thrust. So the other one we know though is the weight force. And those in this situation are the forces acting. So now let's draw the coordinate axis so we can draw our free body diagram. So the tension is going up. That's the direction of the rope, and tension is given with just a capital T and weight is with a capital W. And then weight is pointing down, but we know our acceleration is up, which means our net force is up. And with how vectors work, the vector pointing down needs to be smaller than the vector pointing up in order for there to be a net force up. So we're going to draw the weight force smaller than the tension force. And then we have our situation of, or the free body diagram for a situation of a box being pulled by a rope and accelerating upward. But the next thing to do then is to use Newton's second law to write the equation. So, or equations depending. So that's the net force is mass times acceleration, and the net force is the vector sum of forces. Okay. So here we have the net force in y is equal to the mass times the acceleration. And then we just look at our diagram and we see, okay, tension is pointing up, so we write that as positive, and then weight is pointing down, so we put negative and subtract the weight. And then that way, if we knew maybe what the value of the tension was, or maybe the mass of the object, we could solve for acceleration or tension potentially. Oh, and I also forgot, there's no forces in x, so the net force in x is just 0 newtons. Let's do another example where instead of being pulled up, the box is being pulled to the right and it's accelerating and it's on the ground. So now what forces are acting? So tension and weight are still acting because the rope is still there, still on the earth. This time though, there is a surface that's in contact with, so normal force is also acting. It's funny, these three forces are all the ones where it's their first letter is how they're labeled. So that's nice. Okay, now that we know what forces are acting, then we can draw our free body diagram. So let's take a look though before we do that. So tension, that's going to go in the direction of the rope. So that's going to be going in the positive X direction or to the right. And then weight is going to be down because it's always toward the center of the earth. So that's down. And then normal force is perpendicular to the surface. The surface is the floor, so the normal force is going to point up. So now we can draw. Let's see. So tension to the right, normal force up, weight force down. And then our net force is to the right. And we know that because the acceleration is to the right. So next up, we write our force equations. This time we have forces in X and Y, so we can do more than just say one of them is 0. So the net force in Y is equal to the mass times the acceleration in Y. We'll label it that way. And then our forces in Y, we have the normal force, and then we subtract the weight force because the weight force is down. It's in the negative Y direction, so we subtract it. Cool. And then in X times acceleration in X. And the only force we have there is the tension, and it's in the positive X, so it's positive. And so there's one other thing we can do is we can see, just based on how we established this problem, that the acceleration is fully horizontal. It's not vertical. So what we can end up saying is there's no Y component. So actually the net force is 0. And this is helpful if, for example, we want to know what the normal force is. So we can take this. I'm going to bring it down here. So we have normal force minus the weight equals 0. And if we add the weight to both sides, we end up with, in this case, when there's no acceleration in the vertical direction, the normal force is just equal to the weight. So that's a convenient additional bit of information. And then if we knew the math, and either the acceleration or the tension, we could solve for the other one. And then I think we'll do one more, but this time we're still going to be pulling to the right, but we also have friction. So there's friction now. So the forces, again, tension, normal, weight, and now friction. And to properly define this, let's say we're still accelerating to the right, okay? So now we draw our free body diagram. And remember, when we introduce friction, friction is in the opposite direction of motion. So friction is going to be pointing to the left. But first, let's do normal force going up, weight force going down, and those are the same sides because our acceleration is not in the vertical direction. And then we have our tension force to the right, and then we have friction. And so to know how big friction should be, we just need to remember that our net force and acceleration are to the right. So the tension force needs to be bigger than the friction force. So we'll just draw it like half the size. So, and friction, sorry, is written as just like kind of a curly F. Okay, so that's our free body diagram. And then let's do our net forces again. Net forces in y, mass times acceleration in y, but as I said, there's no acceleration in the vertical direction, so we can just say this is 0. But it's also, looking at our diagram, normal force minus the weight. Okay, and then in x, this time the acceleration is not 0. Mass times acceleration in x. And then we look at our diagram again. So tension is in the positive x, that's positive, and friction is in the negative x. So we put that negative sign there. And that is our two force equations that we got from Newton's second law and our free body diagram. So this is something we'll be practicing. Your post-lecture assignment is going to practice this. What we do in class on Thursday is going to practice it. Because, and I do really want you to try and make sure you understand it. Because this is a super powerful tool for solving force problems. All you need is to know what forces are acting on the object and draw your free body diagram, and then you can generate equations to solve for things. And that just fully comes from the diagram. Anyway, so I think we will leave it here today. I hope you have a great day.